The Existential Crisis Hotline. The Existential Crisis Hotline. The Existential Crisis Hotline. The Existential Crisis Hotline. The Existential Crisis Hotline.
What's up, everybody? Welcome back. Oh, I bumped the mic. Hopefully that wasn't too loud in your ears. All right, so where did we leave off yesterday? Theory of relativity. And that was confusing as hell. Although I think by the end of it, it was starting to make sense. So that's good. I was going to read something. I found this book on my shelf, which I remember reading this when I was probably in middle school. And I just picked it up randomly, I suppose. But it's called Other Worlds by Paul Davies. It's in the subtitle. Is that the right word for it? Space, Superspace, and the Quantum Universe. And it's pretty good. It's pretty good. And I definitely, as I'm reading it, I'm like, I remember reading this, but I don't know how I understood it before. Although it's actually not that hard to understand. It's written for the layman, as they say, the lame man who doesn't know quantum mechanics. But it's like a book that was popularizing quantum mechanics. I'll read the back. Is this the only universe, or are there others? Is the world as we know it a random accident, or is it the outcome of a delicate selection process? In Other Worlds, Paul Davies explores the astonishing implications of the quantum theory of the universe, in which particles can appear and disappear spontaneously. Objects lose their individual identity, and the traditional understanding of reality, in quotes, must be completely revised. Dr. Davies argues that according to quantum theory, the world is a game of chance in which we are not merely spectators but players, and that other universes may even exist along with our own. There may be, in fact, multiple ghost worlds in a superspace of alternative existences parallel to our own. Dr. Davies takes quantum theory to its logical, if hair-raising, conclusions, challenging our assumptions about the nature of time and space, and offering radical new thoughts on the structure of the universe in the light of the most recent discoveries in astrophysics and cosmology. And on the front is a review, those little blurbs, from John Archibald Wheeler. And when I saw that, I was like, how old is this book? And it was written in 1980. So it's over 40 years old. But also on the back is and let's see what Wheeler says. It would be difficult to name any creative scientist of today who writes with the same scope and the same clarity and the same appeal to the wider audience as Paul Davies. And there's also a few other blurbs on the back. I'll read one of them, which is near and dear to my heart. I'll read it first and then I'll tell you who said it. Dr. Davies describes the deepest aspects of quantum theory in a way that is at once luminously clear and tremendously exciting. No one can read it without feeling the thrill of probing the universe to its very core. Who do you think said that? If you guessed Isaac Asimov, you would be correct. So if you're a fan of Isaac Asimov, he approves of this book. Okay, so anyways, there was a really interesting little section. Let me see if I can find it. It's just kind of in the beginning, and I really liked this part. Okay. Let's see. So he gave a little kind of brief introduction into how we got to relativity and then how we got into quantum mechanics, although it's not really details. It's just kind of like a general overview. But there's this one part. I'm just going to read these two paragraphs here. It says, in the earliest days when men and women first began to wonder about the natural events that went on around them, their picture of the world was quite different from ours today. They realized that some events were regular and dependable, like the days and seasons, the phases of the moon and the motions of the stars, while others were arbitrary and apparently random, such as storms, earthquakes, and volcanic eruptions. How were they to organize this knowledge into an explanation of nature? In some cases, a natural happening would have had an obvious explanation. For example, when the warmth of the sun melted snow. But a precise notion of cause and effect was not well formulated. Instead, it must have seemed very natural to model the world on the system that they understood best, themselves. You might be saying, what does that mean? It is easy to see how natural phenomena came to be regarded as a manifestation of temperament rather than causality. Thus, regular and dependable events reflected a placid commitment and benign method at work, while sudden and perhaps violent events were seen as the product of a petulant, angry, or neurotic temperament. One outcome was astrology, in which the order apparent in the heavens was taken as a reflection of a wider organization, linking celestial and human temperament in a unified scheme. That's interesting. In some societies, the temperamental systems crystallized somewhat and became actual personalities. There was the wood spirit, the river spirit, the fire spirit, and so on. The more developed societies constructed an elaborate and strongly anthropomorphic hierarchy of gods. The sun, moon, planets, even the earth itself, were regarded as human-like personalities, and the events which befell them a reflection of well-known human emotions and desires. The gods are angry would have been regarded as sufficient explanation for some natural calamity and appropriate sacrifices made. The power of these grander personalities was taken very seriously, probably amounting to the greatest single sociological force. I could keep reading, but I'd probably just end up reading the whole book out loud. But I just thought that was a really cool explanation. So, okay, how am I processing that? Now, obviously, this is coming from a probably physicalist, reductionistic evolutionary viewpoint. And I'm not saying there's no evolutionary processes, but it's not the whole story. But it is interesting if you look at it just in terms of the development of human thought and thinking, that, humans recognized even back then that they were temperamental. So when they saw things happening in nature, it was like, oh, maybe that's just nature being temperamental. Maybe and then it's like, maybe it's the gods being temperamental. And then that becomes like a singular point of God itself. Like there's a God. And that's very clearly reflected in the Old Testament and the New Testament. Like, God was angry and now he's loving. Like, to the point now where we have modern science, where modern science is like, no, there's no God. It's just evolutionary processes. It's all deterministic. And then you get quantum mechanics coming along. And basically, it's interesting because that statement by Einstein that God doesn't play dice with the cosmos, it's like, did he believe in God? I wonder if he actually believed in God. Let me look that up. I would kind of doubt it, but let's see. I gotta click on this. Did Albert Einstein believe? Oh, there it is. Albert Einstein did not believe in a personal God who intervenes in human affairs or answers prayers. Instead, he subscribed to Spinoza's God. Whoa, I am tiny tonight. Look how tiny I am. What is going on? Whoop, whoa. Whoop. Oh, come on now. Control. Wrong button. Come on. What is happening? Oh, maybe it's option? Oh, yeah, I was pushing the wrong button. Look at me go. Look at me. I'm growing. Okay. Instead, he subscribed to Spinoza's God, an abstract pantheistic concept equating God with the harmony, order, and physical laws of the universe. Okay. So, no God. All right. pantheistic. What's the difference between pantheistic and panentheistic? Pantheism. The philosophical and religious belief that the universe and divinity are identical. It asserts that all is God. From the Greek pan, meaning all, and theos, meaning God. Instead of worshipping a separate supernatural creator, pantheists view the cosmos itself as a sacred, unified, and self-organizing entity. Self-organizing. So, what does it mean that God doesn't play dice with the cosmos then? Because there's no God. It's just the cosmos. What does that even mean? So it's just like a weird criticism. To like reject quantum mechanics because you didn't want to believe God played dice with the cosmos, but you think God is the cosmos. So what does that mean? The cosmos doesn't play dice with itself? Why not? Why couldn't it? Okay, but what do they mean by that? I wrote pantheism. Oh yeah, this is what I was wondering. Panentheism asserts that the universe is contained within God, who is greater than the universe. Ah, interesting. That's interesting. God is greater than the universe. Well, then he's not the universe. That's kind of a weird dichotomy. God plus nature. Okay, so what was I going to say? What does it mean that God plays dice with the cosmos? Because there's this underlying probability. Oh, yeah. I sent this to Sandra earlier. I was looking up what are all the maths that you need in order to study and understand quantum mechanics, like at a basic level to actually understand it. Let's see. Simply, algebra, trigonometry, calculus, complex numbers, linear algebra, differential equations, probability and statistics, Fourier analysis, an introduction to quantum mechanics, because I guess there's specific concepts in math, so you obviously have to have that. Advanced linear algebra and Hilbert spaces, and group theory. Oh, yeah. I forgot about this. What is that? Hold on. Let me send this to my computer. Can I? Oh, I don't have my Wi-Fi on. Interesting. I can text it to myself. I don't have my Wi-Fi on because I use the hardwire connection. Well, I could just show you. Let's see if I need to skip ahead or what. Oh, that's a picture. That's not a video. Where's the actual video? Oh, here we go. Okay, sorry. Let me just skip ahead and find the part. Okay. So what you'll see is a big blurry red dot. And then or let me go back to this view. Can you see those blinking dots? It's not very clear on there. Let me find a way to... Let me text it to myself. What? It's making me... Oh, wait, can I... Oh, no, I can't do that. I was going to try to like mirror my screen, but I don't think I'm set up for that. Well, I'll just show you again. It's not a very clear picture because I was zoomed in with my phone, but I'll just show you one more time. So you can kind of barely see it. It's much clearer if you actually look at the thing, but also there's like a light blaring down on it, so that's probably why you can't see it. No, the psych ward. It was not a UFO. It was a... No, it's not the sun. You guys can keep guessing if you want to guess what it was. No, I took out... Okay. I have a red laser. And it's not because I'm doing DMT laser code experiments over here, okay? I have a red laser for extracurricular activities. Okay, that makes it sound like DMT laser. For it's not a DMT laser. God damn it. I'm not sure if Sandra's asking that because he thought I was saying it was, or if he's wondering what am I talking about. In which case, you need to go back a few streams. No, but it's a combination flashlight slash red laser dot. Okay. Anyways, it's a handheld thing that you can mount upon certain things. Anyways, I got a piece of hair, and we had Katie hold the hair really tight, nice and tight, just like I like it. Okay, and then stop with the comments. You're throwing me off here, man. I'm kidding. I jest. No, so she's holding this hair really nice and tight, real stretched out, real perfectly stable. And then I was shining the laser so that the little thin beam was like hitting the hair, and then you were seeing the pattern. So when you weren't seeing any of those like little dots, it's because I wasn't hitting it quite on the hair, because you have to kind of see where the hair is, right? So I was hitting the hair, and then I'll show you again now that you have the context. I'm gonna turn off my overhead light, because maybe that'll make it more obvious, just for a second. Okay, I'm gonna go dark, guys. Going dark. Here we go. Y'all see it? Okay. So, no, you can't get an unblurred vision. Because I would have to airdrop it, because when I tried to text it to myself, it said it had to do a iCloud thing because the file was too big, because I filmed it in it doesn't look like it, but I filmed it at 30 frames per second, but I had it zoomed in. I should have just not zoomed in, but whatever. So it's very blurry, but it's very clear when you look at it. Trust me, guys, this is not like a UFO thing where I'm like, oh no, if you saw it in real life, it was so clear. Like, no, it's like you could see the dots. I know you could see the dots. Okay, I know you could. Okay, Sandra saw it. All right. Anyways, so that was the diffraction pattern of the laser. I thought that was just cool. You know, I mean, anyone can do this experiment. It wasn't like anything profound, but like you're seeing the dot, and then when it hits the when it hits the thin piece of hair, I tried it also with a piece of thread, like sewing thread, just because it was be easier to like kind of attach to things and so forth, because hair is only so long, and you can't really hold it down very easily. But it didn't work with the thread. It didn't seem to do anything. It seemed to just like block it, I guess, or I don't remember what it did, but it didn't show up. But when I used the hair, you get that diffraction pattern. Like the only reason it was blinking is because I'm like holding the laser trying to hit the light or the hair. Obviously, if I had mounted it, that's what I should have done. I should have got a tripod and mounted the laser to it. I didn't think about that. But anyways, so yeah, you can see the diffraction pattern, and isn't that interesting? It's like interfering with itself, which shouldn't be surprising because it's a wave, but at the same time, why is that happening? Like, if you're splitting the beam, why don't you just see two dots? I don't know. That's weird, right? I didn't really think about that before. I expected to see a diffraction pattern. I just assumed that's what would happen. But now that I think about it, it's like, is this the double slit experiment? Is that what this is? Is this like a very... Didn't we watch a video about this where the woman did that? I think we actually watched a video. I'm acting like it was my idea. Like, guys, I came up with an experiment. No, I know it's because I watched that video, and I was like... we were basically playing with the laser with the cat. That's what was happening, guys. And then I was like, Eureka! What? Did anybody want to give me a piece of hair? And all my kids were like, what are you talking about? I was like, trust me, it'll be really cool. So we got a piece of hair and did all that, and I just already told you all that, so I don't need to rehash that. But yeah, I thought that was pretty cool that you can actually see the diffraction pattern. Like, you can see the bright dots, and you can see the dark, basically blank spaces in between the dots, and they kind of fade out. that was cool. So yeah, I thought that was interesting. Stuff you can do at home, science experiments. How would you do it to see the single way? There's no way you could control one particle at a time. So there's no way you're going to do true double slit. But why does it do that? You know what we should do? Let's ask an AI. Let's ask an AI. Let's see what it says. I'm curious. I'm just reading your stupid comments. You're gonna find my big foot up your laser. All right, it's Drake. I realized that the psych ward was Drake, so now I get to. We have a bit of ribaldry, however you say it, repartee. But it's only one-sided. He doesn't really get to respond. It's just like you have to text, but I get to say it. So it's a one-sided game. All right. Anyways, okay. So I shined a red laser at a piece of hair and got a diffraction pattern on a piece of paper behind the hair. Why does that happen? Instead of seeing two separate beams. What you saw is one of the classic demonstrations that light behaves like a wave. A hair acts like a very thin obstacle. Intuitively, you might expect it to simply block a thin strip of the laser beam, producing two bright regions on either side, but that's not what waves do. When the laser light encounters the edges of the hair, the light wave diffracts around the edges. The light coming from the left edge and the right edge overlaps on the paper behind the hair. Where the overlapping waves arrive in phase... Yeah, okay, we know all that. Yes, we know all this, thank you. A neat experiment to try is a single hair. That's what I did. What did it think I said? AGI, guys. Actually, great ideas. Two hairs close together. A sewing thread. I did that. A razor blade slit. Huh. Why would that do? It would just produce a different interference pattern. A razor blade slit. So it would just go through the slit. Okay, and then it would like fan out, I guess. Two hairs close together. What would the two hairs close together produce? Very similar to a double slit interference pattern. Okay, so what I was seeing was not the double slit pattern. Instead of seeing just a broad diffraction pattern, which is what I saw. No. Instead of seeing evenly spaced fringes, you'll see a broad diffraction pattern. I don't think it's going to look anything like that, though. Hey, guys, it's trying. It's trying. I said a piece of hair. But anyways, I'm arguing with the chat again. I gotta stop. That must be what it's like to be schizophrenic. You just have a chat in your head that you argue with. Crazy. One hair, diffraction pattern. Two hairs, diffraction pattern and interference pattern. Many evenly spaced hairs, like a comb, a diffraction grating with very sharp, bright spots. Two hairs taped parallel. Yeah, I just didn't have any tape, but a millimeter or so apart can produce surprisingly beautiful patterns on a wall several feet away. I don't think this is possible, but let's just see what it says. Is there a way to do a similar setup to produce the particle aspect of the double. I doubt it. I really doubt that's even possible, but why not? Yes? The particle aspect of the double slit experiment doesn't show up as a different pattern. It shows up in how the pattern is built up. Right, that's the problem. Yeah, so you couldn't really practically do it because you can't fire one photon at a time. Extremely dim lasers, yeah, so I wouldn't be able to do it. Yeah, because how are you going to observe a single photon? You're just not. I'll just look at it behind the slit, behind the hair. I'll just look at it and see what it does, see if I can detect it. Well, anyways, that's interesting. Okay, so let's look at... Ah, okay. Hey, we're talking to an AI, so why not? Somebody asked if they can share the stream in the Kik community. No, definitely not. Do not do that. I do not want any attention. Okay. What is the conflict between... I can't see what I'm typing. Oh, I'm not typing. I'm not typing shit. I'm typing in the chat. What is the conflict between... I'm just going to write QM because I'm cool. Oh, I'm going to write WM. QM and relativity theory. Okay, check this out, guys. It's one of the biggest unsolved problems in physics, but it's important to distinguish between special relativity and general. Okay. So, quantum mechanics and special relativity were largely reconciled. The result is quantum field theory. The real conflict is between quantum mechanics and Einstein's theory of gravity. Okay, so this is where the point is. So I'm not just going to read this because then it's like I'm just reading what an AI says to you. I'll go, how's that different than just watching a video and talking about it? Okay, you know what? Fuck that. What's the difference? This is just built from other people talking anyways. So general relativity says that space and time form a smooth geometric fabric called space-time. We talked about that last night. Matter and energy curve space-time. We didn't really get into that. We didn't watch the general relativity stuff. Maybe we should do that. Gravity is a curvature. So gravity is not a force. It's the space-time fabric warping, and that's what gravity is. So you're moving, and then you're moving in a straight line, but because the space-time continuum is warped, you move in a straight line towards whatever is causing that warping, which would be like a mass or something. A common analogy is a bowling ball deforming a stretched rubber sheet. Problem with that analogy, from my perspective, is that assumes gravity in the first place. That's why it warps it, but yeah. So if you can imagine, space-time is like a 3-dimensional, 4-dimensional fabric. Okay, so here's the problem. In general relativity, space-time itself is the stage on which physics happens. In quantum mechanics, everything seems to fluctuate. So what happens when space-time itself must fluctuate? Near a black hole singularity or the beginning of the universe, gravity becomes extremely strong. Okay, I'm going to stop reading this fucking thing. Okay, so, all right. We haven't talked about black holes. Like, that's the problem. We haven't talked about black holes. Let's look up what a black hole is. There's just so much context. What is a black hole? Okay. I was just waiting for you to say something, Drake. I wasn't going to say it. A black hole is a region in space where gravity is so intense that nothing, not even light, can escape. So if light can't escape, then there can't be any information. If light can't escape. Okay. So if light can't escape out of a black hole, then you can't know what the hell's going on in there. That's step 1. Step 2. Remember we talked about the uncertainty principle? And let me tell you about the Schwarzschild radius. Is it Schwarzschild or is it Schwarzschild? Swarthy. Yeah, it was Schwartz. The Schwartz. I see your Schwartz is as big as mine. All right, Schwarzschild. A child of the Schwartz? It's a parameter to the Schwarzschild solution to Einstein's field equations that corresponds to the radius of a sphere in flat space that has the same surface area as that of the event horizon of a Schwarzschild black hole of a given mass. So when you think of black holes, you think of a big giant thing. I know you do. I know everyone does. I know when you're thinking about black holes, you're thinking of that they're gigantic. What happened to my... Hold on a second. What happened to my... Oh, I clicked on Chrome. I thought I was on Chrome, but I'm not. I was on Firefox. Okay. So when you think of black holes, you think of these ginormous, gigantic things, right? But did you know a black hole can be very small? The Schwarzschild radius is basically like, okay, given this amount of mass, the Schwarzschild radius tells you how close, let's just say, to that mass would you be where light can no longer escape. So if you have a lot of mass really concentrated into a small point, or you have a lot of, what is mass equal to, class? E equals mc squared. So mass is energy. If you have a lot of energy concentrated in a very small space, that could represent an amount of mass. And the Schwarzschild radius could be very small. Okay? I think I've got that right. So, remember uncertainty principle? To really get really close to look at that particle with that amount of energy, you'd have to have a lot of energy coming in there, a high frequency of light, a very small wavelength, otherwise you can't see it. And when you put that much energy into it, that would represent the threshold for that Schwarzschild radius, and therefore you create a little black hole. Now, I don't think it implies it's going to suck the universe into it. I think it just means you can't get any information out of it. I don't know what that really had to do with what I was talking about earlier with the contradictions about quantum gravity, or well, not quantum gravity, quantum mechanics and relativity theory, but yeah, no, it does have to do with it, because that would imply that there's discontinuities. Like, oh man, do you guys know do you know what continuity is in mathematics? I'll show you a simplified version. Okay, so these are functions, or graphs as some of you might call them. And you have four types of discontinuities. I don't really understand this oscillating one. Unless those are really sharp points. But the general idea, this is not the mathematical precise version, but the general idea is, if you draw the graph and there's a hole in it, meaning the only way you can get from one side to the other is to jump over a hole. That's in the removable discontinuity. I'm talking about this one here. Well, you can't see it. Yeah, it's the one on the left, the blue one. That would be a discontinuity. Also, the infinite discontinuity. So you have this vertical dashed line as an asymptote. So the function's value is going higher and higher and higher on one side, but on the other one it's going down, 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 down. They're never going to meet. So there's like a gap you can't get from one part of the function to the other without somehow crossing over a gap in the function. Jump discontinuity. How did it know I failed my last calc quiz? A jump discontinuity, you can see it's just another version of the same idea, just all the different possibilities, right? So here, it's the function actually has a value there at that point. It just doesn't agree with this part of the function. So on the jump discontinuity. So in the first one in A, there is no value of that function. So like if you tried to plug in A, the value A, into the equation for that function, you would not get a number. It's not defined. But for the jump discontinuity, you would get where that filled in red circle is. Watch this. I'm pointing at this one. However, on the removable discontinuity, you don't get any value. But on this one, you do. Okay? You guys like that? I just thought of that. It's pretty funny. Oh, man. Okay. Okay, so in other words, there's like a hole of some sorts. There's a gap, okay? But the whole idea behind space-time is that it's one continuous fabric. There's no like holes in it. Or there's another kind of discontinuity. It's not even just discontinuity, actually, okay? Because now you got to understand derivatives. Because to illustrate the next point, I have to teach you a little calculus. Okay, you guys ready for that? Discontinuous derivative. Okay, we're gonna look at some calculus here. Here we go. Oh, it's the same website. Thank you, Jen. Appreciate that. All right, here we go. You guys ready? We do some calculus. Now, actually, you don't really need calculus, but these are calculus concepts. So you've got this red function here, and then you've got this blue one here. Now you could define these as one whole function if you wanted to. You could just make that one blue and that one blue, and it's all one function. So they don't have to be two separate. They have two different equations, but they don't have to be. You could write this as what they call a piecewise function. You could say this part of it is described with this equation, and the other part is described with this equation, and it's all one function. Okay? So imagine this is all one thing. Now you'll observe that there's a little V down there. Yes, as Drake so kindly pointed out, this is the absolute value function. Okay, so there's that little point where they meet at 0 at that little V. Okay, now check this out, all right? You ready? The slope of the red one is a negative slope because as we move to the right, I can't tell if you guys are seeing me move to the right or the left because it's not mirrored. So I think you would see it. Well, I'm watching the video right now, so I would know what you're seeing because you're seeing what I'm seeing. And I'm moving to the right. Okay, wait, no, I'm moving to my left. Whew, that's confusing. Okay, let me ask you guys a question. Am I moving my hands to the right or to the left? What do you guys think? Okay. You think I'm moving it to the left? Let's think about it, though. Okay. Where do they put logos on shirts? On the right or the left breast? They put them on the left. You see? The left. So this is the left. You see? And this is the right. This is the right. Now I'm moving to the left. Because the thing is flipped. Okay. However, if you look at the diagram, if I go this way, that's to the left, even though I'm actually pointing to my right. That's all I'm talking about. It's just, it's like mirrors, right? Okay. Anyways, so here we go. Oh, I can do this. This is much easier. So as we go along here, here we go. As we move this direction, on this line, we go down. So that's a negative slope. And as we keep going to the right on this one, we go up the escalator. My finger's not cooperating. Okay. So the one on this one has a positive slope, and this one has a negative slope. I'm like, was that necessary to explain? Yes, it was. Okay. Now, here we go. Here's the pop quiz. What's the slope at this point here? Ooh. The slope of this one is -1. The slope of this one is +1. You know, because for every 5 units to the right, it goes up 5 units here. I know I'm estimating, but you could plug it in. What's 5 if you plug it in for x equals 5? Because the f of x equals the x. So if you put 5 for x, then the f of x is 5. So the point 5 comma 5 right there. So, and it starts at 0, 0. So if it went over 5, it went up 5. So that's a slope of 1 because you divide 5 by 5. This one has a slope of -1 for the same reason. So, let me do this one. This version is easier. This has a slope of -1, and this has a slope of +1. What is the slope at this point? What is it? Tell me what it is. You don't know. Actually, Drake already said. It's undefined. Yeah, there is no slope there. Because you have to understand how slope is actually defined in calculus. It's very loosely whatever the slope is coming in and whatever the slope is coming out. That looks like I'm doing it the other way. But you get what I'm saying. Whatever it is coming into that point and whatever it is coming out of that point, or coming in from both directions, let's say, right? If that's not the same slope coming into the point, that's a problem. You can't define the slope there. They call it the derivative, right? But the derivative doesn't have a value. And watch this. Oh, you guys are going to love this. Okay. Online whiteboard. Is this the one I used last time? Start a whiteboard. No sign up required. For 24 hours. Okay, cool. All right. Goodbye. Here we go. So, oh, that's terrible. That was terrible. A line. Oh, an arrow. Check this out. Oh, I have to do it again? Are you kidding me? That's really weird. I should have done this differently. I'm just going to do lines, guys. Oh, I can type L. That's nice. Okay, L. Here we go. There's one. There. Oh, this is so bad. I'm typing L and then it's just popping that up. That's not helpful. All right, I'll get this down. Don't worry, guys. We'll get it sorted out. There's probably a way easier way to do this. Can I copy something? Oh, I can't do that. There we go. Look at that. And then I can move this guy over here. All right. We're cooking. All right, so I'm going to do a freehand drawing. So here's that one. Oh, no. That's terrible. Line again. So here's that one. And then let me do another one. Bam. Okay. Let's assume it's the same graph. Sandra, I always have a book ready. Okay. Yeah, go read Freedom. Oh wait, you can't because you don't have it yet. Too bad. All right. Now check it out. So the slope of this one, if I were to graph it over here, okay. So we've got f, and then that's that original function we were looking at, and this one's going to be called f prime. That's what they call it. Oh, that looked weird. It looks like that, f prime. That's the slope of this thing. So I'm going to graph the slope of this one. All right. Here we go. Well, it's -1 from basically all the way back from negative infinity up to here. I know you don't see the rest of it, but you have to stop drawing it somewhere. So if this is -1 here, come on, just give me this. If that's -1, then the slope would look like this if I graphed it. If that's -1. What's the slope of this one if I graphed it? It would look like this at 1. But what's the slope in the middle at 0? It doesn't have one. So it would look like there would be a hole here, and there would be a hole there. Do you see that? So I'm just showing you how you would represent that visually. So the slope, if I were to graph the slope, what does it have? It has a jump discontinuity. Is that a jump? No. Or is it removable? No, it's a jump. I don't know. I don't know what it's called. I don't care what it's called. It's a discontinuity. You see, there's no value there. So my point is that when you look at the slope of something, you can have a discontinuity. Even though it doesn't look like, if you look at the original graph here, it doesn't look like there's any discontinuities there. But when you look at the slope, there is, okay? So if you can imagine space-time, right, moving around, looking all wavy and stuff in 3 dimensions and stuff, right? Or even just imagine like a surface, all like with, dips and troughs and tops and all that stuff, right? But can you imagine when it's curving, right, there could be like a really, 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 really steep point like this, okay, like a really pointy point, where if you were to look at the slopes coming into that point, there would be a discontinuity there in terms of the slope. Like whenever you see a sharp point, there's a discontinuity. There's other ways too, but this is one example. Okay. So a discontinuity, I mean, there's like a hole there. There's something missing in a way. There's no information there. So if a black hole like sucks everything into it and you can't get out, you see how that could be like a discontinuity. So if you can create a black hole in space-time, that means it's discontinuous. So I'm just guessing here. Like, this all makes sense to me. And I would think maybe that's why there's a problem between quantum mechanics and relativity. Because in quantum mechanics, you have the idea of light as a wave, and, well, it's in relativity too. But you have the uncertainty principle, you have all that, and you have the Schwarzschild radius and all this business. So I would assume if you have a discontinuity there, light can't get out, it gets sucked down infinitely, like, right? Then that could cause a hole in some abstract sense. So then maybe that's why relativity theory doesn't agree, because it's like, no, there can't be any discontinuities. Let's see if that's the case. Let me go back to my ChatGPT. Let's see what it says. In general relativity, blah, 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 near a black hole singularity or the beginning of the universe, gravity becomes extremely strong. Quantum effects become extremely important. The equations stop making sense. The center of a black hole. Yeah, general relativity says space-time is a smooth, dynamical geometry. Smooth. Quantum mechanics says everything physical exhibits uncertainty and fluctuation. When space-time itself becomes subject to quantum fluctuations, our current mathematical frameworks stop working. So I'm just trying to give an intuitive idea that's based on a little bit of math of how math can show you that there's fluctuations. There's information you don't have. Now, I don't totally understand what it means by fluctuations in this context, But let's look that up. Maybe we can find out. Quantum field theory. Let's look. Quantum fluctuations explained. Neil deGrasse Tyson. Empty space is not empty. The vacuum. The quantum vacuum. Quantum fluctuations. Oh, there's a video just called that.
I want you to go ahead and imagine an ideal vacuum.
Okay.
A vacuum with absolute...
I'd say an ideal vacuum. It's not too heavy, easy to take apart. You know, when you suck up like marbles or random shit, you can get them out easily. It doesn't get stuck in the hose.
no matter inside of it. And I want to ask you, what is inside the vacuum? Intuitively, there's nothing inside of but empty space.
Right.
But what is actually really profound is that empty space is not actually entirely empty.
Doesn't that... Oh. Well, I was going to say, doesn't that kind of contradict the whole there's no ether thing? Because they were like, there's no medium. And then they're like, oh, actually, empty space isn't empty. There's still something fluctuating in there. Maybe it seems like you're back to the... But maybe that's why. Maybe it's like almost like implying there's like an ether-like aspect, which the whole idea about light is based on the idea that there isn't.
In fact, quantum field theory, a major part of quantum mechanics, the science of the really small, suggests that empty space is actually teeming with a sea of virtual particles coming into reality and popping out of reality like the static on a television screen. And these particles help explain many phenomena, even describing how black holes, the most powerful sources of gravity, can evaporate over time.
What?
And I believe it may explain gravity itself. But what are virtual particles, and where do they come from? Imagine empty space as a series of points. If you add energy by introducing particles or photons to one of the points, it will oscillate with that amount of energy, back and forth in a harmonic motion, affecting points of space around it. The Heisenberg uncertainty principle states... Imagine
Sorry,
empty...
guys, I was busy pouring tea all over the floor. It's this Stanley thing, dude. Like, when you try to pour out of it, it just like... I guess you have to just take the lid off. That's the problem. I'm not taking the lid off. I was assuming they're designed so that you can open it a little bit, and that's clearly not the case. I haven't learned my lesson, and I probably still won't. Okay.
Space as a series of points. If you add energy by introducing particles or photons to one of the points, it will oscillate with that amount of energy, back and forth in a harmonic motion, affecting points of space around it. The Heisenberg uncertainty principle states that knowledge of two related variables, such as momentum and position, is limited. A version of the uncertainty principle relates energy and time, where the information for both is limited. If we combine our definition of space in a vacuum and the uncertainty principle, then we can conclude that the points in space will follow...
I lost track because I was looking at that H. And I was like, doesn't that look like somebody bowing down to the cross? I need to back up, guys. Sorry, I gotta back it up. I gotta make sure I understand what's going on here.
Imagine empty space as a series of points. If you add energy by introducing particles or photons to one of the points, it will oscillate with that amount of energy,
Okay.
back and forth in a harmonic motion, affecting points of space around it.
Okay.
The Heisenberg uncertainty principle states that knowledge of two related variables, such as momentum and position, is limited. A version of the uncertainty principle relates energy and time, where the information for both is limited. If we combine our definition of space in a vacuum and the uncertainty principle, then we can conclude that the points in space will follow the uncertainty principle and never have energy equal to zero. In this picture of a vacuum, space is a sea of swirling points in space that constantly changes, causing what are called quantum vacuum fluctuations, where the energies of all the points in space constantly switch between different energy levels by oscillating back and forth. These fluctuations in energy in the vacuum become vacuum energy. Yeah, this is quite weird how energy can exist in empty space and not in actual particles. But what's even more interesting is that this concept can be proved mathematically. Let's look at what's called a quantum harmonic oscillator. Don't be discouraged by
So is this where all these 0-point energy people get the idea that you can tap into it?
the name. It's just a graph that shows possible energy levels of the vacuum energy described earlier. Every escalating n adds an extremely small amount of energy to the vacuum called a quantum. What is really interesting about this diagram is what is called the 0-point energy, or the energy of the ground state, the lowest possible energy.
I had to give him a like for that. 0 point. There's 0 point to understanding this, but we're going to do it anyways.
Allowed in a quantum system. From this point up on the graph exist real particles, like electrons. No real particles can exist below the 0 point. The energy lower than the 0 point energy is so low that it cannot exist in real particles. Everything in this area below the 0 point is actually just disturbance in the vacuum energy that we call virtual particles. It is important to note that virtual particles are not actually real particles, but rather just disturbances in the vacuum energy that can push the vacuum energy described earlier over the 0 point energy. Virtual particles must arise in pairs. With a matter-antimatter pair, vacuum energy can manifest itself in tiny particles of matter and antimatter that can arise spontaneously and annihilate themselves almost immediately after they are created. A virtual photon pair can also arise spontaneously and annihilate, despite having no rest mass. An important thing to note is that the more energy contained in the virtual particles, the less time they have to exist. As previously stated in the Heisenberg uncertainty principle, the knowledge we have of the energy,
they're indirectly proportional, so if one goes up, the other has to go down.
And the time of a quantum system is limited. If the time is significantly less than h bar over 2, the value of the lower limit of our possible knowledge of both variables, then the energy must be very great in order to bring the value high enough to obey the equation. Conversely, if the energy is significantly less than h bar over 2, then the time the virtual particle exists must be very great. Another important thing about virtual particles is that they can take any energy and even have attractive and repulsive forces associated with them. But wait, if virtual particles aren't real, then how do we know they exist? There are many ways that virtual particles affect real matter. The experiment that helped postulate the appearance of virtual particles was the Casimir effect experiment. If you take two uncharged metal plates and put them around a micron apart and put them in a vacuum, then they will close together. Why? For any photon to appear.
So this is an established effect, apparently. So all these people doing 0 point stuff, they're not retarded. They're just trying to figure out a way to engineer something to take advantage of it. But it's not like they're just, oh, you believe in 0 point energy. It's like, no, it's like apparently a part of quantum mechanics.
It must complete at least half a phase within the given distance. A small amount of...
I always kind of assumed that it was an assumption that there's energy in the vacuum, that like it was like a belief based on like some conspiracy theory type shit. Not that they're literally like, no, like in quantum mechanics, it says that there's vacuum energy and we're just trying to figure out how to do it, how to extract it somehow.
Space exists between the plates, limiting the wavelength. Virtual photons that are created between the plates will therefore have a limited range of energy. Wavelengths that are too long cannot appear between the plates. However, outside the plates, any energy a virtual photon can appear. As a result, the pressure from the virtual photons on the outside of the plates is greater than the pressure on the inside of the plates, and the plates are pushed together. Virtual particles are also fundamental to our understanding of black holes. On every black hole, there exists an event horizon, which is the invisible border between the inside of the hole, where gravity is so strong that even light is not able to escape it, and the outside, where light is just fast enough to escape the black hole's gravity. Stephen Hawking
Okay, I'm just thinking, so it's not that the speed of light's changing, it's just not fast enough to escape. Okay, because of the gravity. Because the gravity actually bends the light. Okay.
postulated what is now known as Hawking radiation, which tells us the mechanism of how a black hole can actually evaporate. On the surface of the black hole, there exist virtual particles everywhere in pairs. Sometimes, when a virtual particle pair appears, one of the virtual particles crosses the event horizon, and its pair becomes a real particle because it cannot annihilate itself with its pair. Where does the energy it took to convert the virtual particle into a real particle come from? The black hole. At a very slow rate, as energy is taken away from the black hole loses mass and can potentially evaporate.
So light can't escape, but energy can escape.
This video is brought to you by Brilliant.
Wait, did I skip
Click the
something?
link in the description to
What the heck just happened? Was that the end of the video?
I want you to go ahead and imagine
That was the end of the video. Okay. Why is it that light cannot escape a black hole, but when a virtual particle enters one without its pair, energy can escape? Maybe it's just a misunderstanding of the word escape in this context. Hawking radiation. It's not that light is trying to fly outward. Inside a black hole's event horizon, space-time is curved so extremely that all future directed paths lead inward. It's not that light is trying to fly outward and gravity pulls it back. Okay, I mean, that makes sense. Like, it's just all the paths go in. At that. Okay. Okay, I can understand that. So rather, general relativity, the geometry itself is arranged so that outward is no longer a future direction. I think I get that. How does Hawking radiation escape? The radiation is not created inside the horizon and then escaping. That would be impossible. Okay, so my intuition was valid. Instead, the radiation is generated by quantum effects in the region near the horizon. The popular story goes, you know that old tale that Pappy used to tell us around the campfire? A virtual particle-antiparticle pair appears near the horizon. One falls in, one escapes. The escaping particle becomes real radiation. But this picture isn't literally what's happening. Okay, good, because it didn't make sense. The modern explanation is that quantum fields near the horizon behave differently for observers far away. What the hell does that mean? Quantum fields near the horizon. Oh. I thought it meant... Okay. I thought it meant that the field near the horizon behaves differently for someone far away. I'm like, what does that even mean? It just means a field that is near one is different than one that is far away. So if you're an observer in either case. Got it. Okay. The black hole alters the vacuum state of the quantum field. Okay. What looks like empty space near the horizon does not look empty to a distant observer. The result is that particles are observed coming from the vicinity of the horizon. In the full calculation, there's no need to imagine a particle physically climbing out from inside. The radiation originates from the quantum field outside or straddling... Oh. Okay, I mean, that makes sense. Like, it didn't originate inside the thing in the first place, obviously. But I guess the confusing part is the assumption that, which it seemed like he was implying that, so you have the two virtual particles. The one that becomes real doesn't enter the black hole. The one that enters the black hole is no longer, it's gone. And so they can't annihilate each other because this one can never get back out, and then energy is produced. But how would it know that its partner got lost? And then it creates energy. So probably that's not what's happening. Probably the particle is the energy. That's probably what's happening. This is the fascinating part. So where does the energy come from? The escaping radiation carries positive energy away. To conserve energy, the black hole must lose... Oh, but it is... The escaping radiation... Maybe escaping is a weird word. It's just not getting sucked in. To conserve energy, the black hole must lose energy. Losing energy means losing mass. The black hole slowly shrinks. So the escaping radiation, I'm assuming so far, is just the real particle that was created. Perhaps. And energy doesn't escape the black hole. It just loses mass. Which would shrink the Schwarzschild radius, which would allow any of the mass to then escape as energy, I suppose. Losing energy means losing mass. The black hole slowly shrinks. Near the horizon, relativity allows a peculiar bookkeeping trick. Okay, why does the negative energy particle story appear? One can mathematically describe the infalling partner as carrying negative energy relative to an observer at infinity. The negative energy contribution reduces the black hole's mass. Oh. I mean, from that perspective, it makes sense. We don't know what any of those words mean, but negative energy would be like negative mass. You're adding negative energy, so it like equals a reduction in the mass because they're balanced out. This is a useful way of thinking about the... Yeah, that's what I was thinking. It's not literal. This is a useful way of thinking about the calculation, but it shouldn't be taken too literally as tiny particles being created and one somehow... So it's not literally tiny particles being created. Or is it just somehow one sneaking out? I didn't think something was sneaking out. I was asking about the energy. Didn't I say energy? Or what did I say? Yeah, I said energy can escape. I didn't say the particle can escape. Before Stephen Hawking, black holes were thought only to absorb things. After, they became thermodynamic objects with temperature, entropy, and radiation. This eventually led to the famous black hole information paradox, which remains one of the deepest questions in theoretical physics. The short answer is light cannot escape from inside the event horizon because all future paths point inward. Hawking radiation does not escape from inside the horizon. Instead, quantum fields near the horizon create radiation outside the black hole, while the black hole loses an equivalent amount of energy, and therefore mass. Is the energy being created outside the black hole just the real particle that didn't enter, or is it a separate point? This is where the popular virtual particle pair story starts to break down. If you take the popular picture literally, then yes, you'd imagine... it makes sense why it's confusing, because then it's not the real picture. It's all mathematics, and they just use words to describe an analogy. A particle-antiparticle pair appears, one falls in, the other remains outside, the outside one becomes a real particle. In that story, the escaping particle is the same particle that never crossed the horizon, but the actual quantum field theory calculation doesn't really describe events this way. The deeper picture is that particles are not fundamental objects in the calculation. What's fundamental is the quantum field. The black hole changes the structure of the field near the horizon. What one observer calls vacuum, another observer can describe as containing particles. The Hawking radiation emerges from this change in the quantum state of the field, so there isn't necessarily a unique moment where this specific virtual particle became that specific real particle. Instead, the outgoing particle is a part of a global quantum process involving the field around the horizon. A rough analogy. Imagine a calm ocean. At first glance, there are no waves. Then a current changes the conditions and a wave appears far away. Asking which water molecule became the wave isn't quite the right question. The wave is an excitation of the whole system. Similarly, Hawking radiation is an excitation of the quantum field. One reason, okay, it's just energy bookkeeping. They're not actually particles. What's really interesting is that the outgoing Hawking particle is not completely independent of what fell in. In the standard derivation, the outgoing radiation is quantum mechanically related, entangled to modes associated with the horizon. This is what leads directly to the black hole information paradox. I think we should look that up. Is the energy just the real particle that didn't enter? In the popular explanation, yes. Okay, so my intuition was correct based on the story. In the actual quantum field theory description, not exactly. The outgoing particle is better thought of as a quantum excitation created by the altered vacuum state around the horizon. Interesting. So it's like you have a proton and an antiproton. The antiproton gets lost, so it can't annihilate the proton, but it's really just a disturbance in the field, and it basically, wow, it's actually kind of weird if you think about it. When the black hole eats one of the virtual particles, it gets smaller. That's an interesting, that could be a riddle. I'll give you guys this one for free. What gets smaller when it eats? Although I don't know, maybe it's only specific to virtual particles. Okay, let's look at this black hole information paradox. This looks interesting. The black hole information paradox is an unsolved problem in physics and a paradox that appears when the predictions of quantum mechanics and general relativity are combined. The theory of general relativity predicts the existence of black holes. Oh. I was kind of assuming, I just never really thought about it. I was assuming that the black holes was coming from the quantum mechanics side, but now that I think about it, it makes sense because they're dealing with large masses and energy. Okay, we'll keep going. Black holes, regions of space-time from which nothing, not even light, can escape. So maybe my whole thing about the calculus and the discontinuities was wrong, but I don't know. I feel like there's something to that. In the 70s, Stephen Hawking applied the semi-classical approach of quantum field theory and curved space-time to such systems and found that an isolated black hole would emit a form of radiation, now called Hawking radiation in his honor. He also argued that the detailed form of the radiation would be independent of the initial state of the black hole and depend only on its mass, electric charge, and angular momentum. The information paradox appears when one considers a process in which a black hole is formed through a physical process and then evaporates away entirely through Hawking radiation. Hawking's calculations suggest that the final state of radiation would retain information only about the total mass, electric charge, and angular momentum of the initial state. Since many different states can have the same mass, charge, and angular momentum, this suggests that many initial physical states could evolve into the same final state. That's a problem because a function can't have a bunch of initial inputs that give you the same output. Therefore, information about the details of the initial state would be permanently lost. It's like if I said, If you give me $5, I'll give you a hot dog. If you give me $10, I'll give you a hot dog. If you give me $30, I'll give you a hot dog. Okay, so 3 different people give me money, and I give them each a hot dog. Okay, and then I erase how much they gave me. And they're like, someone else observing it sees the people with the hot dogs, and they're like, how much did that guy pay? I'm like, well, he's got a hot dog. They're like, right, but I can't tell based on that how much they paid because they all have the same thing. That was a terrible analogy, but it gets the idea across. Therefore, information about... Okay. However, this violates a core precept of both classical and quantum physics in that in principle only, the state of a system at one point in time should determine its state at any other time. Interesting. It just made me think of that Douglas Hoffman thing. I'll come back to that if I can. Specifically, in quantum mechanics, the state of the system is encoded by its wave function. The evolution of the wave function is determined by a unitary operator, and unitarity implies that the wave function at any instant of time can be used to determine the wave function either in the past or the future. In 1993, man, it's not that long ago when you think about it, Don Page argued that if a black hole starts in a pure quantum state and evaporates completely by a unitary process, the von Neumann entropy of the Hawking radiation initially increases and then decreases back to zero when the black hole has disappeared. This is called a Page curve. It is now generally believed that the information is preserved in black hole evaporation. For many researchers, deriving the Page curve is synonymous with solving the black hole information puzzle. But views differ as to precisely how Hawking's original semi-classical calculation should be corrected. A measure of the statistical uncertainty within a description of a quantum system. Oh, where'd it go? If a black hole starts in a pure quantum state and evaporates completely by a unitary process, the von Neumann entropy decreases back to zero. Initially increases the Page curve. They don't even talk about it on here. Page curve is the time-dependent evolution of entanglement entropy that rises during black hole evaporation, peaks at the Page time, and declines to preserve unitarity. Yeah, the math is getting out of hand here. Huh. Okay. Interesting. I was looking at this concept earlier called Markov chains, which is kind of an interesting concept. In probability theory and statistics, a Markov chain or Markov process is a stochastic process, right, which means a random process describing a sequence of possible events in which the probability of each event depends only on the state attained in the previous event. That's why I was thinking for a moment earlier, because when it was saying about the black hole... Oh, did I click off of it? No. Where is it? Right here. In principle only, the state of a system at one point in time should determine its state at any other time. But with Markov chains, it doesn't seem like that's the case. What happens next depends only on the state of affairs now. let's see, what was this? Markov chains explain. Let's see what this says.
When you type a message on your phone, it suggests the next word before you finish typing. When Google ranks billions of web pages, it decides which ones matter most. When a weather forecaster predicts tomorrow's conditions, they often start with today's. These seemingly unrelated problems share a common mathematical foundation, a framework for reasoning about systems that evolve randomly over time, where the future depends only on the present, not on how you got there. This idea has a name. We call it a Markov chain after the Russian mathematician Andrei Markov, who first studied these processes in the early 1900s. Markov was interested in a deceptively simple question. If you know the current state of a system, how much of its history do you actually need to predict what happens next? His surprising answer was that for many systems, you need nothing beyond the present moment. The past becomes irrelevant once you know where you are now. This property, known as memorylessness, might seem like a severe limitation. How can a model that ignores history possibly capture the complexity of real-world systems? Yet Markov chains turn out to be remarkably powerful. They model everything from DNA sequences to stock prices, from queuing systems to language itself. The key insight is that while these systems may have rich histories, their immediate future depends primarily on their current state. And that simplification makes analysis tractable without sacrificing too much accuracy. To understand Markov chains precisely, we need three ingredients: states, transitions, and probabilities. The states are the possible configurations of the system. For weather forecasting, the states might be sunny, cloudy, and rainy. Each day, the atmosphere exists in exactly one of these states, and our goal is to predict how it will evolve. The transitions describe how the system moves from one state to another. From sunny, the weather might stay sunny, become cloudy, or turn rainy. Each transition has an associated probability, and the probabilities leaving any state must sum to 1, since the weather has to be something tomorrow. We can organize all these probabilities into a transition matrix, where each row represents a starting state and each column represents an ending state. The entry in row I and column J gives the probability of moving from state I to state J in one time step. For our weather model with 3 states, this is a 3x3 matrix with 9 probabilities that encode the...
Oh. I just understood something. Okay. I just had to pause for a second because I just something just clicked. Interesting. Okay. All right. It's got nothing to do with this per se directly. It's got to do with the Douglas Hoffman thing, but I think I'll play that next because just now it makes sense what he was saying, and I see the significance of what he was saying. So we'll come back to that, but I'm going to keep going here for a moment. Okay, so you have 3 particular things that could happen. These are your 3 options. And depending on where you're at, there's a certain probability that you could stay the same. You could go to one of them or you can go to the other one, and each one has a different probability. Now, how do you come up with these probabilities? I don't know. Perhaps that's based on observing things in the past. I don't know. I don't know how you come up with the probabilities. Maybe he said it, but I was probably thinking about something. If he did. But let's assume you could calculate probabilities, or you could know them somehow. Then the matrix is simply the recording of each of the options with their probabilities of transitioning to the next option or staying the same in depending on the context. So if you look at this, let me get my pointer. Oh wait, no, I gotta get. Why is that so hard to do? If you look at that 0.7 there, that's the probability of being in state S and the next state still being in state S, 70%. The probability of being in state S to begin with and then becoming cloudy is 20%. And I don't know if the rows are the initial state and the columns are the next state, or it's vice versa. I didn't hear that part, but you get the general idea. I would assume it's the rows, but yeah, it doesn't really matter. It probably does technically, but it doesn't matter intuitively.
Complete dynamics of how weather patterns evolve. What makes this a Markov chain is the memoryless property. The probability of transitioning to the next state depends only on the current state, not on the sequence of states that came before.
I'm just thinking about this in the context of like algorithms predicting things about human behavior and like states and moods and things like that, and emotions.
If the weather is sunny today, the probability of rain tomorrow is the same regardless of whether yesterday was sunny, cloudy, or rainy. The atmosphere has no memory beyond its current condition. We express this idea using conditional probability. The probability of being in state J at time n plus 1, given the entire history up to time n, is equal to the probability of being in state J at time n plus 1, given only the state at time n. In other words, the full history reduces to a single value that represents the current state. This reduction or compression is what makes Markov chains analytically manageable. Let's make this concrete by simplifying our weather model. Instead of 3 states, suppose we have just 2, sunny and rainy. When it's sunny, there's an 80% chance it stays sunny tomorrow and a 20% chance it rains. When it's rainy, there's a 60% chance it stays rainy and a 40% chance it clears up. We can write this as a two.
I want to clarify something first. Where's my chat GPT? Do I have it up here? I don't know what happened to it. Okay. Regarding Markov chains. What's the question I'm trying to ask? The future state only depends on the current state based on a set of probabilities relating the first, the initial state, to the possible next states. But two questions. One, how are the probabilities determined? It probably depends on the context, but whatever. And two, are those probabilities not complicated encodings of past states, even though they are still only probable? I don't know if that makes sense what I'm asking, but we'll see what it says. It probably understands what I mean. The probability of the next state depends only on the current state. It's literally saying sunny and rainy. That's weird. Maybe because that's the classic example. Maybe it watched that video. Not, or whatever, you know what I mean. Maybe it was trained on it. Not because the past doesn't exist, but because the model assumes that whatever information from the past matters has already been compressed into the current state. Okay, I get that. How are the probabilities determined? Measure them from data. Suppose you look at 10,000 days of weather records. Yeah, I mean, that seems obvious. That's what I was thinking. derive them from a theory. Okay, obviously. Aren't these probabilities really encoding past states? Yes. Okay. The answer is often yes. Okay. Suppose I tell you current state weather is sunny. That might not be enough information. The chance of rain tomorrow could depend on humidity, air pressure, wind direction, temperature, all of which reflect the past. If I ignore those variables, my probabilities become averages over many hidden histories. So, the probability of tomorrow being sunny is really the probability of tomorrow. Oh, the probability of what tomorrow is based on it being sunny is really the probability of what happens tomorrow based on it being sunny and all the hidden stuff I didn't include averaged together. A true Markov state is richer than it first appears. Physicists often enlarge the state until it contains everything relevant. Velocity carries information about the past. Then the system becomes Markovian. This is common. Oh, instead of just using position, they use position and velocity. Oh, that's interesting. But there's the uncertainty principle. So they're using position and velocity, but you can only know one. Confused I am. The system, okay. A useful way to think about it. A Markov state is really a sufficient summary of the past for predicting the future. The past hasn't vanished, it's been compressed. Imagine a chess game. The current board position contains information about everything that happened before. You don't need to replay every move. The current position summarizes the relevant history. This connects to my philosophical question. I asked earlier whether states might... Oh, that was in a different conversation. It remembered. Okay, well, I'm not going to get into that because I want to get into that later, but... Okay. I still feel... Okay. So, yes, in a way, the probabilities are encoding the past, but not like in a deterministic way, because it's still probable. Because just because it's sunny... see, but that's the question. Like, if you could know all the variables, wouldn't you be able to perfectly predict it? But not if quantum mechanics says that there are no actual But if it already happened in the past, then it was already an observed thing, so it would have had already a determined state. I'm just going to ask it, how does the uncertainty principle come into play regarding the position velocity point? In classical mechanics, a particle state is often taken to be xp, position momentum. If you know both exactly at one instant, then in principle you can predict the future exactly. The state is Markovian because the current position momentum completely summarize everything relevant about the past. But you can't know both. So, okay, but it is Markovian because whatever state it's in should determine the next thing. Okay. Not necessarily because it should determine it. It's just that it completely summarizes everything relevant about the past in the current state. That's, I think, what makes it Markovian. Quantum mechanics changes this dramatically. The uncertainty principle says that the change in x and the change in momentum, it's limited by the... What is that h thing? That was the Heisenberg thing? Is that what that's called? What is that one actually called? What is the h with the cross? h bar. Oh, it's Planck's constant. Okay, yeah. I was thinking that initially, but I wasn't certain. Okay, yeah, Planck's constant. Okay, yeah. So it basically has to do with Planck's constant, which, for context, is obviously it's a proportionality constant because that's what we were just seeing. It's a fundamental physical constant. A photon's energy is equal to its frequency multiplied by the Planck constant. Oh, well, there you go. A particle's momentum is equal to the wave number of the associated matter wave multiplied by the Planck constant. And then there's the Planck's length. That's more what I was thinking of. Did they talk about it? Anyways, the Planck length is like the smallest unit of length possible, and beyond which I guess you can't. Let's just look that up. Planck's length. Planck's length. The smallest theoretically measurable distance in the universe. And then there's another one, Planck time? What was the word? Planck duration? Planck duration? Is that? I don't even know what the word would be. Planck time. Okay, yeah, just time. The smallest theoretically measurable unit of time. Okay, all right, so back to this. So it's just Planck's constant. This means that there's no quantum state in which both position and momentum have perfectly definite values simultaneously. I don't understand why it says that, why that implies that, but I mean, it does seem to indicate that the change in one would require a small change in one would require a big change in the other one. So maybe that's why it's related. The classical state cannot be the fundamental state of reality. There you go. The classical state cannot be the fundamental state of reality. So the fundamental state of reality cannot be that things have a fixed position and simultaneously a fixed momentum. So instead, quantum mechanics uses a wave function, or more abstractly, a vector in Hilbert space. The wave function contains all the information available about the system. The crucial point is, the wave function is the Markov state, not the particle's position and velocity. So now that makes more sense. Because I was like, how are you going to make a Markov state out of position and velocity if they're not both determined together? And they're like, you can't. You got to have a wave function. Given the wave function now, quantum mechanics tells you how it evolves into the future. You don't need earlier wave functions. It's starting to make a lot more sense. Let's look up wave function. Quantum, I guess. I don't know if that's the right word, but quantum wave function. No, it's just wave function. It's a mathematical description of the quantum state of an isolated quantum system. Okay. The Schrödinger equation determines how wave functions evolve over time. Wave functions are complex valued. Let's see some examples. I want to see an example. Okay. For now, consider the simple case of a non-relativistic single particle without spin in one spatial dimension. More general cases are discussed below. According to the postulates of quantum mechanics, the state of a physical system at fixed time t is given by the wave function belonging to a separable complex Hilbert function, or Hilbert space. As such, the inner product of two wave functions... Okay, so they're two separate wave functions can be defined. Okay, so they define... Oh, this is the inner product of two wave functions. Okay. What is the... Is that psi? What is the psi star? Maybe they explained that before? I get this. The state of such a particle is completely described by its wave function. The square modulus of the wave function. Okay, so that's just an equation that's a square modulus. But what is this psi star? Is interpreted as the probability density for a measurement of the particle's position at a given time t. You see, so it's like they're not defining a specific state. They're defining a probability density for the position. Oh, the asterisk indicates the complex conjugate. Okay, so it's just a function on the same one. Okay, that's what I was trying to figure out. If that was supposed to be a separate, different function, but it's just the complex conjugate of that, which is just like a mathematical operation. It's like saying, it's not saying this technically, but it'd be like saying square it, or, take the square root or something. It's just a operation on that. Interesting. For one spinless particle in one dimension, if the wave function is interpreted as a probability amplitude. I keep seeing that word pop up in the other stuff I'm reading. The square modulus of the wave function is interpreted as the probability density for a measurement of the particle's position at a given time. Man, look at this. You'd have to know all this probability theory. But to me, I'm assuming that means that is essentially the position of it. Like, not technically, but it's like the probability density, meaning where it probably is. Okay, there's actually a lot of context there. Okay, but I think we're understanding that intuitively. Okay, so the state is a wave function. In both cases, the future depends only on the current state. What is different is what counts as a state. The uncertainty principle tells us that exact position plus exact momentum is not a valid quantum state. The wave function becomes the deeper object that carries the information needed to evolve the system forward. Yeah, this is one reason some physicists say quantum mechanics isn't merely adding uncertainty to classical particles, it's replacing the classical notion of state itself with something fundamentally different. What is this? Did we already see this? No, we didn't see that one. Okay, I'm just thinking whether I want to look at that Douglas Hoffman thing or not yet. I think there's enough context for that. I think there's enough context for that now, is what I meant to say. Let's just see.
simply.
Okay, let me go here.
He had his monadology.
Actually, let me back up because this is actually pretty interesting here.
Now, our best scientific theories are physicalist theories. We assume that space and time are fundamental. Einstein's general theory of relativity, and that objects inside space and time are fundamental, particles, quantum fields. And in that framework, what you said wouldn't hold, right? So, but what we have to do then is look at the current scientific framework, and there's a problem with it. The problem is the nature of observation. So one of the biggest problems in quantum theory is the so-called measurement problem. And the problem there is evolution of states of systems seems to follow one rule, the Schrödinger evolution, when you're not looking, and a different rule when you look, the so-called collapse. The act of observing a system somehow seems to be important in the evolution that you see. So Schrödinger evolution when you're not looking, collapse when you look. There's no that idea has been around for literally a century. A century.
Yeah, literally. I think it was 1927 or something.
Yeah, 1926 was
26,
Schrödinger.
that's right.
Yeah,
Yeah.
Schrödinger. So 1926 Schrödinger revolution. Yeah. I think 25 for Heisenberg's, but
right.
So it's been about a century, and there is no satisfactory solution to this so-called measurement problem in quantum. There are proposals, but none universally accepted, and all of them have serious.
I want to see what he means by the measurement problem. The measurement problem. Let's see what the AI says. The quantum measurement problem is the fundamental puzzle of how a microscopic system existing in a probabilistic state, a superposition, instantaneously collapses into a single definite reality when observed. Standard quantum equations like the Schrödinger equation describe a physical system evolving continuously as a wave. That's so wild, actually. It's not, but it is. Which means particles like an electron can simultaneously exist in multiple places or states. And that's the thing about it. It's like, it's not that you don't know where it is, you just don't have enough information. It's that it's existing in all of those states, and all the probabilities of those states is interfering. And I think that's what the probability amplitude is about. However, when we conduct an experiment or take a measurement, the system's wave function suddenly collapses. We always measure exactly one distinct outcome. But the math gives us no explanation for how or why the wave selects the single state and discards the rest. To understand why this is one of the most perplexing mysteries in modern physics, the continuous evolution. According to the core equations of quantum mechanics, everything in a system unfolds smoothly and predictably. The collapse measurement introduces a sudden, random, and irreversible event where all potential possibilities vanish except for the one observed. The missing rule. The theory perfectly calculates the probabilities of which outcome will occur, but fails to define exactly what constitutes a measurement or how the physical collapse is triggered. Over the past century, physicists and philosophers have proposed various interpretations of quantum mechanics to explain the mechanism behind this problem. The Copenhagen interpretation, the most widely taught, suggests that a quantum system does not have definite properties until it's measured. It doesn't have definite properties. In this view, the wave function is merely a mathematical tool for predicting probabilities rather than a physical reality. And asking what a particle does between measurements is considered meaningless. And that's what Heisenberg was saying in that book. The many worlds. This view argues that the wave function never collapses at all. Instead, every time a measurement is made, the universe splits and all possible outcomes of the superposition are physically realized across an infinite number of branching parallel realities. That sounds wild. Objective collapse theories. These theories propose that the collapse is a real physical event that occurs naturally once a system reaches a certain scale or mass, bridging the gap between the quantum and classical worlds. But how does it reach a scale? How does it reach a mass? I'm sure there's some theory there, but that would be my question. Hidden variables theories. This framework assumes quantum mechanics is incomplete and that particles actually possess definite predetermined properties governed by hidden variables that we cannot currently measure, making the randomness only an illusion of our ignorance. Doesn't it kind of blow your mind that it's 2026 and the smartest people in the world, if you want to call them the smartest people in the world, still don't know how reality works. And yet we know how to drive a car. We know how to build things, but we still don't understand how it works. Why, fundamentally? What is it? Okay, let me go back to this. So that's the measurement problem.
Problems, and I'm happy to talk about them and their problems, but...
Well, even the Copenhagen interpretation is so... It's just saying that the measurement, collapses the wave function into an eigenstate or whatever. What does that mean? I always find it so interesting that you have these, pop quantum physics people now, Sean Carroll, who, by the way, I'm a big fan of his books. I think he's amazing. But these, Neil deGrasse Tyson, some of these people will definitively say things like, oh, when particles collide, they collapse into an eigenstate, or the quantum detector is what's collapsing the wave function into an eigenstate. And I think it's totally unfalsifiable. What if the superposition of the observation exists in the quantum detector, and then your interface, your conscious interface, is collapsing that? We can't say that definitively. There's no way to know exactly what's collapsing the wave function. So it's all faith-based assertions.
Well, and the key problem at the core of this whole issue is that we don't have a notion of an observer and the process of observation. That's what's missing. And if you think about it, that's not a minor point. What is science? Science is the systematic gathering of data through observations. We call them experiments. We systematically observe the world, and then based on our observations, we write down mathematical theories about what we think are the structures of the world. And we hope that somehow it's legitimate to think that our observations give us the kind of information that we would need to write down useful, perhaps accurate theories about the structure of the world. But for this whole thing to work, observation has to somehow genuinely inform our theories of the world. So the question is, what is observation? Why should we believe that human observations will genuinely give us the kind of data we need to come up with legitimate theories about the world? That's a non-trivial question, and to date, science cannot answer that question. So what we have is this really interesting situation where we know that observers are not unimportant. They're central, and we don't have a theory.
They're unremovable.
They're unremovable. Without observers, there is no science, and there's no reason to believe our theories. And our theories...
But that's not the current... The current paradigm is that we live in this materialist, reductionist world where our consciousness and we are happy accidents of atoms that happenstance bounced off of one another and coalesced.
And that your awareness, your consciousness, your subjective experience, let's say, is like an illusion. I think that's the basic conclusion of the reductionist physicalist viewpoint, is your experience is not real, it's an illusion. But then, and we talked about this on the stream before, like, that's a big weird thing to think of, right? Your experience is not real. Well, it's real to you, but then the question is, well, who is the you? What is the you? Are you just your experience? Or is your experience happening to you? And if it's you, then what is the you? Because can you separate yourself from your experience? Not hypothetically can you, but can you? Can you actually, in fact, right now, separate yourself from your experience? Like, and yet, when you go to sleep, yes, you dream, but at a certain period you're not dreaming, and then you wake up in the morning and you're still here. So what's going on there? Who is the you? Who is the self?
To like these conscious agents or whatever, this emergence is this popular term today.
Right. And so what we'd have to do then in that story, what you have to do is to show how that account could still lead to some notion of an observer that could give you data that would...
Yeah, like, in other words, if it's just physicality from a reductionistic perspective, and we evolved from molecules that were not conscious, consciousness is an emergent phenomenon, if that's the case. Consciousness, we could also say awareness, but it's kind of difficult to describe what's the distinction there. But let's just call it consciousness for now, because that's what it would be called in the reductionist physicalist viewpoint. That your consciousness is an emergence from the complexity of the form you're in, and it probably didn't exist before in any context. It evolved to this state, and this is like the highest state of evolution as a human being, and your consciousness emerged from that. And what he was saying is, let me go back, because he was making an important point about you have to still figure out where the observer comes from. Oh, yeah. But how does, if it's the reductionist viewpoint, the physicalist viewpoint, okay, you can say, well, if that's your assumption, then of course you have to conclude your consciousness emerged from this complexity. You have to assume that, because there's no other possibility. But what he's pointing out is, but then you still are obligated to explain, how does it emerge? How does the observer even come about in that process? And I don't think science can, not science, but the physicalist viewpoint can't, because it just discounts the observer as primary to the whole thing in the first place. Now, I don't agree really fundamentally with where Douglas Hoffman takes the point. Why does this say AI there? That's weird. I don't think it's AI. I wonder if maybe they use some AI in part of it or something. Sorry, got distracted there. He kind of takes it to a different point, which is, well, actually, I won't speak for him. I'll let him continue, and then we can talk about that maybe after.
Legitimately constrained theories about the nature of reality, and no one has done that yet. That's just, there's no accepted theory. So there's the measurement problem in quantum mechanics, and then there's also the problem in studying just human observations, right? Where we're trying to say, okay, human observations, like I'm observing that I'm tasting water or something like that. So that's an observation. I'm tasting water, and we're trying to come up with, okay, a physiological description of the brain and brain activity that would be that would give me the necessary and sufficient conditions to say that was an observation of Hoffman drinking water. That was Hoffman observing drinking water. We've been at this for decades, actually for longer than that, but seriously for several decades, trying to understand how we could explain human observations like colors, tastes, smells, and human
subjective experience, I think, is another way of saying what he means by observation. Because observation is not the written description of what you observed. It's the actual, I was going to say physical, but experiential experience of the observation. It's not just like, okay, I observed this cup. Cameron observed a cup. Right, there's my observation. No, that's not my observation. That's a description of my observation. My actual observation was the experience of observing it, right? So that's the part where that part can't be explained, is how does that come about? That subjective experience point, the subjectivity.
Observations in terms of either functional properties of some kind of network, computer network or whatever, or neural network properties of the human brain or something like that, or microtubules, collapsing of microtubules, or integrated information patterns and so forth. We've been trying to give a theory about observation, and I know the people who are doing that, they're brilliant. They're my friends. We're buddies.
Still doesn't work though.
And
it still doesn't work because it only describes we looked at this a while, maybe like a few days back or a week back or something, where it was, I forget what we were looking at, and it was saying something about, I think we were talking to like Google's AI or something. It was making the point about it's like you have the sense data, you have the sensory information coming in, that becomes electrical signals in some way depending on which sensory organ is receiving the information. It gets sent to the brain is processing that. Okay, cool. That's as far as current science can go. And it's like, see, look, we explained how the brain did it. And it's like, well, that's still not answering the question of, but the part after that where I experience it, like where is me, the subjectivity part coming from? I don't know how I can explain it even more clearly because it's so obvious. It's something we take for granted. And we're so used to objectifying. And it's like, well, look, your brain processes the information and then you see it. But no one usually questions, like, because I'll say, do you see the cup? And they're like, yeah. I'm like, but you don't see the cup. You see some kind of experiential. You have an experience of it. But how is that experience being generated? Because it's not from the cup itself. It's not from the light bouncing off the cup. It's not from the chemical electrical signal going through your body. It's not from your brain processing it. Maybe it is, but okay, but then how does it then create an experience for you? And what is the you that's experiencing? And okay, even if you can explain how it produces the experience. For example, you can understand how the computer produces the pixels in this certain pattern based on what you're looking at. But the computer isn't having a subjective experience of that, we assume. And if it is, then fuck, everything must be. If you're going to say the computer is experiencing itself subjectively just like I am, then you would have to assume everything is. Because why is the computer sufficiently... Right? Because you could say it in the same sense of like a... because it's just LEDs on a screen. You could... I'm trying to think of how I could explain that in another way. It's really not that different than a painting. A human being put the dots of paint on the canvas and then you look at it, right? So you could say how that picture is produced, but that's not the same thing as when you're looking at the picture, you're experiencing the picture. Again, I don't know how to put that into clearer words. Maybe it is clear, maybe it's not. I don't know. You guys can tell me if it's not clear what I'm trying to get across, or maybe you could just say like, yeah, I relate to what you're saying. I get what you're saying.
There's not a single specific observation that they can account for, like the taste of mint or the smell of, chocolate or something like that.
So you're trying.
See, even sort of trying to make it about the taste of chocolate or the smell of mint. That's fine, but also you have like a total immersive experience that's not just one thing, like one taste, one smell. It's all of this, the visual, the sound, the feeling of the air on your body, right? And you could say, well, but look, you can produce a virtual reality device and it does the same thing. No, it doesn't. Because that's not explaining how I am experiencing it. You're just saying how the picture is displayed. So it doesn't explain what's the thing observing. And how is it observing? How is it experiencing it? There's the experience that's being generated, but then there's the thing experiencing the experience. And the thing that's experiencing it, that's the part that's like not accounted for at all in any of these theories.
Trying to apply math to literal human experience.
That's right, because that's the foundation of science. If we do not have a human observation, we have no data for our scientific
agree.
theories.
Not only that, but you have collapse of the quantum wave function. There's no way to even know which eigenstate, which particular state gets picked. That's all based on probabilities.
Right.
And so there's no way to predict, let alone like some subjective experience of water or like seeing a color or an animal or whatever. Like that feels like way above our pay grade. We don't even know about like the position and momentum of an atom or a subatomic particle, an electron or something.
I completely agree. And I should point out that what I'm saying here is
that's actually a pretty profound point that Jesse Michaels is saying, is like, dude, it's not even about the taste of the mint. We can't even tell what's making the electron in that state with that momentum. We can't even tell what's collapsing the probabilities into that particular state, let alone anything else. At the most fundamental level, we can't even tell how that's happening or why.
prior to the issue of consciousness. So there are colleagues of mine who say that conscious experiences are an illusion.
There you go.
It's, they're a construct of the brain.
It's funny because I feel like that's actually what he's arguing. He hasn't made the argument yet, but I don't see any, and as we'll watch more, maybe I'll process it a little more, but everything he says from this point on, I don't see how he actually accounts for it either, actually, but we'll see. Maybe I'm the Markov thing was interesting, and he's going to talk about that. That's why we looked at this, but let's just keep going.
And that's perfectly fine. If you want to say that, that's perfectly fine with me. There's the attention schema theory, for example, that says this. But then the question is...
Well, yes, okay, yes, but even then, even if it's an illusion, like, I can observe an illusion, right? So to say that my observation is an illusion, what the hell does that mean? The self isn't even real? Well, I don't agree with that. Like, do we agree with that? Like, are we real? Are we actually here? Are we actually... It's like going back to Descartes. I think, therefore I am. Which I'm not saying it's because I'm thinking, but don't we intuitively believe that because I'm having an experience, I must exist? Unless that's not true. Or perhaps what you are is something more fundamental and the experience is being added to it. But even then, it's like there has to be an experiencer, is what I'm saying. But the claim there would just be like, no, it's just the experiencer is an illusion. There's no experiencer. It's like, well, that's fucking weird, right? So this is all an illusion. No, not this is an illusion. Not the things I'm seeing are an illusion. My experience of it itself is an illusion. Okay, so then what am I? That would be the question you would naturally think, right?
Is okay. We're interested in science, not just hand waves. So I want a specific, mathematically precise attention schema for the illusion of the taste of chocolate, or the illusion of the smell of chocolate, or whatever it might be. So I'm a hard-nosed scientist.
It's a good point. Like, even if it is an illusion, explain how the illusion is produced. Again, not the picture, but the experience itself. You're saying the experience, the experiencer is an illusion, but how is that illusory experiencer being produced? You can't explain that by saying how the pictures are produced.
To understand the foundations of observation, because it's the foundation of science, and forget consciousness, just call them, consciousness is an illusion. Fine. I still need to understand how observations work. So how exactly does the illusion get done? And the answer is there is zero on the table. there is not a single scientific theory about the illusion of mint or the taste of chocolate.
So how do you?
So we're nowhere on this. Is really, it's stunning.
Yeah.
Here it is, 2026, and we have no theory of observation. And observation is the foundation of everything that we can do in science. And what we need is a theory of observation that's not only precise, but that will lead to theories that say that our understanding of observation does the right thing, because we need coherence, right? Whatever our story about observation is, it has to be coherent and say that, oh yeah, this theory does allow that observation gave you legitimate data to build the theory.
So how do you think observation works?
Shit.
So I think that if we start inside a physicalist framework, we're not going to close that loop. I think for a couple of reasons, but I think there's logical problems. But also I know the players in the field, they're brilliant. I mean, they're really brilliant. These are smart people. They're coming up empty. When I try to do it, I come up completely empty. I just think it's not going to work. Someone can easily prove me wrong by giving one. But right now, there's nothing on the table.
I think we're in the Stone Age on it. I don't see how, with math, which is so primitive, how you could ever come to encapsulate something so kind of visceral, and I'm not using multi-dimensional in a scientific way, but multi-dimensional as like just experience, everyday experience seems to, it's even like, think about neuroscience, which obviously you're well versed in. You have these disparate pathways of speech and reading comprehension and, auditory listening. And then you have this binding problem. And so that's even, you can barely explain the pathways with math. You can't.
Right.
So then why can, and then we have the binding problem where we can't explain the seamless perception of experience. So, at an even lower level, how can we explain everyday experience with math? I just think we're, going to be in the dark for a long time there.
Right, and so there are two problems I think you're pointing to here. One is that the math could be very, very complicated. The neuroscience is very, very complicated. So maybe, that complexity itself is just standing in the way. And I agree. But I think in addition, there is a principled problem. I think that if you don't start with observation, you're not going to get it out of your theory. Now, this is something that Leibniz suggested back in 1700. He had his monadology, and Leibniz proposed that the fundamental furniture of the universe are these monads, which were observing entities. And so there were a bunch of these different kinds of observers, and they were all linked together with what he called a pre-established harmony. So there was observation, and then there was some structure binding all these observers together. But we didn't really have the math. I mean, we had Newton's math. We could do, time evolution theories, and differential equations and so forth. So we did what we could. Leibniz had this idea, but he had the math that could do the Newton kind of thing, but he couldn't, they didn't have the math, the probabilistic math that we really needed to do his thing. And more recently, John Wheeler, very, very famous physicist, worked on gravity. He invented the term black hole. He was, Richard Feynman's advisor. He was in the who's who of physics. He came to the realization later in his career that somehow we had to start with what he called observer participants. That somehow the observer was really a critical notion that we were missing, and he felt that once we got that notion down, got it really rigorous, that we could then build up our physics from that. And I agree with Wheeler. I think that, so he had this very famous paper in 1989. It was called the It from Bit paper, informally the It from Bit, that somehow it's information of some kind that you get from observation that's going to be used to construct what we call the physical world. And I think that he's onto something. And I've been pursuing the very, very same thing. So I've been looking for 40 years for a mathematical model of the observer as foundational. And actually, Wheeler cited my work in his It from Bit paper.
Really?
So I've got a book called, so I've been after this, so this is not a new gig for me. I published a book in 1989 called Observer Mechanics, with Bruce Bennett and Chetan Prakash, two mathematicians. And so, I've been after this observer thing, not just this last week or two. It's been 45 years I've been after it. And so Wheeler cited that book as an example of the kind of thing to start to pursue. And then I've continued to pursue it because it's a deep problem. And now I just in the last 2 years, so it's not like we've just started, but in the last 2 years, we've really had a breakthrough that I can tell you about, where we start with the notion of observer. We can make it rigorous, and then we can start to ask, how do we build space-time as a headset? And then start to explain all these other weird phenomena that we were talking about earlier.
Well, I want to get into that. To tell me about it.
Okay. So he's about to get into it. So I will leave that for tomorrow, because it's already late, and I want to be able to really stop and talk and everything. And if I do that over the next 20 minutes, this is going to go till 1 a.m. So we'll leave it at that for tonight. But man, that was interesting. It's good that we covered the Markov stuff, because he's going to talk about this. And when he talked about it the first time, I was like, I don't know what the hell he's talking about. I mean, I kind of understood based on what he said, but since we kind of looked into it a little bit more deeply, it makes a lot more sense now. That's what I was realizing earlier. So I'm more understanding what he's getting across. So we'll get into that tomorrow and see where that takes us, because I think it's quite interesting just to see where. Now, he's not a physicist; he's a cognitive scientist, but he's bringing in the cognition, the more of the observer side. It makes sense, right? But yeah, okay. So I'll leave it at that, guys. Appreciate y'all in the chat with all your spicy comments, and we'll see you tomorrow night. Bye, everybody.